Hi, I am Muhammed Ali Koşal. In engineering design course, we developed a RISC-V processor. Our team has 3 members and one academic counselor.
Hi, I am Mert Kaya. There is a need for computation in every field where technology is used. Designing the processor rather than purchasing it ready-made gives the user the freedom to optimize the processor for specific purposes like artificial intelligence and image processing. Processors with RISC instruction set architecture have a large slice of the processor market share in these days. Processors with RISC instruction set, which are mainly used in embedded and mobile systems, are becoming available for personal computers and cases requiring high processing. The best known of these open source architecture is the RISC-V architecture. Here we can see MIT's technology reviews article highlighting the importance of the RISC-V architecture. We also participated in Technofest chip design competition this year. We can also see Chuckle here, which is the Aselsan's domestic RISC-V architecture-based processor project. Engineering requirements are shown here. It must support RV32 IM-AFB ZISKIR instruction set manual, support UART peripheral, should have a 4KB level 1 cache to hold instructions and data. It should be utilized and tested on Nexus for DDR FPGA and VGA LCD screen for application.
Hi, it's Muhammed Furkan Kırdı. Here you can see the project plan that we implemented during the project period.
Let's look at the implementation details. In level 0 design, we have a UART input and output for communication and clock signal for synchronization and a power supply and the output for the main memory. In design architecture, we have 3 main parts. The first is the UART for communication and the L1 cache and its controller and the core. The core is the main processing unit. It has a circuit on figure. We start the developing from the Harris and Harris digital design book, and we add the new units and the connections for new instruction sets. The core and L1 cache interaction, we have 2 separate cache for instruction and the data. We have a direct mapping policy and a write-back algorithm. In UART communication module, it's a very common used serial communication protocol. The wishbone interface is a bus algorithm. And the memory architecture, in the detailed memory architecture figure, we can see the control signals and the data connections. We use the Xilinx Vivada tool for both synthesis and the simulation, and the Verilog HDL is used in the projects.
Now, I will give you some information about testing and outputs of the processor we designed. We verified our processor in 3 different ways. These are simulation part of Vivada application, theoretical calculation with reference to some books, and after the selecting a frequency suitable for these 2 results, we run our design on FPGA board. First of all, our requirements were divided into units. Each unit was designed and handled separately and checked with the test codes on the Vivada simulation. When any problems occurred, corrections were made immediately. It's very important to get this part right before doing FPGA and theoretical calculation. Here, you can see the design of the I instruction and the result of the test we have done. Our first aim in the project is to complete all requirements. The requirements are optimized to run faster after the design stage is over. Here, you can see the multiplication, atomic, floating points, ZISC, bit manipulation instruction, and also UART communication design and test results. After which, the whole system was merged. This stage was the most difficult part of the project. To test the final version of the processor, we run the code you see on the screen and analyze the outputs. Then we made some theoretical calculation with the reference to books to determine the frequency of our processor. We run our processor on the FPGA board with the frequency we determined according to these calculations and simulations. To understand more clearly whether the code is working correctly, we displayed the register information of our processor on a screen. After these three verifications are finished, all our requirements are proven to be successfully designed.
In the cost analysis part, we must first learn what NRE means. NRE refers to one-time costs associated with the initial development and manufacturing of a specific integrated circuit. These costs include expenses for designing the ASIC, creating masks for manufacturing, and testing the produced chips. NRE costs are incurred upfront and remain constant regardless of the production quantity. In terms of cost, FPGAs generally have lower initial and non-recurring engineering costs, making them more suitable for small to medium production volumes and scenarios requiring rapid prototyping. However, FPGAs may have a higher per unit cost, and their potentially higher power consumption could lead to increased operating costs over time. On the other hand, ASICs are more cost-effective for large production volumes due to economies of scale, offering lower per unit costs. However, ASIC development involves higher upfront expenses, longer development cycles, and greater risks of financial loss if the project is altered or cancelled. The choice between FPGA and ASIC depends on factors such as project scale, time to market requirements, flexibility needs, and balance between upfront and per unit costs. The graph clearly shows that after a volume of 4K units, ASICs are starting to be more cost-effective. Therefore, despite the fact that the ASIC project requires 146K in NRE, after 4K units, the ASIC is starting to return the investment compared to an FPGA. Commercialization plan for our RISC-V architecture-based chips involves highlighting the breakthrough features, highlighting its versatility, focusing on advertisement, trying to reach the target audience, forming strategic partnerships, participating in education initiatives, offering technical support, listening to compliance and feedback. Thank you for listening.
Thank you for your listening.